Welcome to our 29th session. In this session, we're going to be flipping over from the left side of the device structure tree onto the right side. And the first device that we'll be studying is the NMOS metal oxide semiconductor structure. On the left side, we were looking at things like diffusion constants, diffusion currents, diffusion lengths, recombination times, minority carrier diffusion equations. Here we'll be looking at very similar to metal semiconductor, drift currents, majority carriers, electric fields, permittivities. So it's going to take us back to where we were when we studied the MS structure. So today we'll just introduce, we'll have a little bit of motivation and formation of the MOS structure. We'll be talking about band bending in the MOS structure, give some examples, and finally, if we have time, we'll start on something called threshold. But first, let's listen and look at one of the really magical moments in Hollywood from Rodgers and Hammerstein's The King and I.
We've just been introduced. I do not know you well, but when the music started, something drew me to your side. So many men and girls are in each other's arms. It made me think we might be similarly occupied. Shall we dance on a bright cloud of music? Shall we fly? Shall we dance? Shall we then say goodnight and mean goodbye? Or perchance, when the last little star has left the sky, shall we still be together with our arms around each other? And shall you be my new romance? On the clear understanding that this kind of thing can happen, shall we dance? Shall we dance? Shall we dance?
Why do you stop me? That's pretty.
No. Your Majesty, I didn't realize I was, after all, I'm not a dancing girl. In England, you know, that is a girl would not dance while a man was looking at her.
Ah, but she will dance a strange man holding hands, etc., etc., etc.
Not always a strange man, sometimes a very good friend.
Good. We dance together. You show me. You teach, you teach.
The polka, it's very simple. You just count. And 1, 2, 3, and 1, 2, 3, and 1, 2, 3, and 1.
Shall we dance
1, 2, 3, and
on a bright cloud of music? Shall we fly?
1, 2, 3, and
Shall we dance?
1, 2, 3, and
Shall we then say goodnight and mean goodbye?
1, 2, 3, and or perchance, when the last little star has left the sky.
Shall we still be together with our arms around each other? And shall you be my new romance? On the clear understanding that this kind of thing can happen, shall we dance? Shall we dance? Shall we dance?
1, 2, 3, 1, 2, 3, 1, 2. I won't get hand. This time I will. 1, 2, 3, and 1, 2, 3, and 1, 2, 3, and stand it. 1, 2, 3, and 1. You can throw me off count.
1, 2, 3, and 1, 2, 3, and 1, 2, 3, and 1, 2, 3, and
No, it's not right.
No, you were doing it.
No. It's not the way I see Europeans dancing tonight.
Yes, it was. It was just
No.
like that.
We're not holding two hands like this.
No, as a matter of fact.
like this. No?
Yes.
Come.
These are some of the topics we'll be covering today. Of course, we're just looking very briefly at the device structure tree. We're on the right side now. And then we'll be talking a little bit about the MOS structure, the metal oxide silicon structure, in a qualitative sense. We'll be talking about how we form this structure, and then we'll be looking at some of the mathematics behind the structure and what it all means. And hopefully, towards the end, we'll be able to at least mention, or if not, starting our next session, this idea of threshold. Okay, so this again is the device structure tree. We're on the majority carrier side. This is the minority carrier side. Minority carrier diffusion equation, things like diffusion constants and recombination times and all things like that. Here we're on the drift current side, so we won't be having too much to say about minority carrier diffusion equation. Now this is the structure. We have a metal and we have a silicon. The predominant structure that we'll be looking at in the MOS is P silicon, just like when we had the dominant structure for the PN junction and for the bipolar junction transistor. Generally the P was on the left, N was in the right or in the middle, and P was on the collector. So for the BJT, we generally looked at the PNP structure, whereas for the MOS, we'll be looking generally, not always, but generally at P-type silicon, and we'll see the reason for that a little bit later on. So the first question we ask, and it's a reasonable question, does this thing look like a metal semiconductor, a Schottky barrier, or does it have more in common with just a transistor, not a transistor, a parallel plate capacitor? Both of these are structures that we've seen previously. The parallel plate capacitor is relatively straightforward to analyze. We've analyzed the Schottky barriers in previous sections, and then the question is, which one is it more like, or is it not like either of them? Is it unique? Okay, so first let's look at the metal silicon structure. In the Schottky structure, when I bring the metal in contact with the silicon, and if it's rectifying, that's generally the important case, there is an equilibration in Fermi levels, there is a transfer of charge across the junction, and that transfer of charge results in a depletion region as the two Fermi levels, one in the metal and one in the silicon, come together. In this structure, there can be no transfer of charge across the boundaries because there is a huge barrier. This gate oxide here has a barrier of about 9 electron volts. There's no way that charge can transfer from the silicon into the metal. So in short, the oxide layer really does matter. So it is not a Schottky structure, although it has certain characteristics in common in the energy band diagrams, but it certainly is going to be much, much different than the metal silicon structure. Well, how about the parallel plate capacitor? In a parallel plate capacitor, we have a metal or the bottom electrode rather than silicon. Well, one can argue that if we have heavily doped or even moderately doped p-silicon, this is a fairly good conductor. The problem is that in a parallel plate capacitor, when we apply a voltage, apply a bias between the two metals, it doesn't matter what the sense of that bias is. We could apply minus to the top metal, or we could apply a positive bias to the top metal. The capacitance is only a function of the structure. In an MOS type structure, and p-silicon, if we apply a negative bias to the top metal, we're going to attract holes. Minus up here will attract holes, and that will be pretty much like a parallel plate capacitor. Minus on the top electrode and positive on the negative electrode. However, if we put a positive bias on the metal in an MOS structure, we're going to repel holes. So that is very different from the parallel plate capacitor. In fact, we're going to form a depletion region. As we push holes away from the surface between the gate oxide and the silicon, we're going to form, not deform, form a depletion region right close to the surface, and that does not happen even remotely in a parallel plate capacitor. So it's not like the MS structure, and it's not like the parallel plate capacitor. Neither of them works. It is unique, it is challenging, and I hope it will be fun. Okay. The other thing that we're going to be dealing with here is that when, up to this point, in 28 sessions, we've had a lot of new words. Starting with session 29, all of a sudden, we throw a bunch of new words at us. Or I should say, a bunch of new terms are thrown at us. And I've written down some of these terms: accumulation, depletion, flat band threshold, immersion, NMOS and PMOS. These are terms that we're going to have to work with, become familiar with, and first we're going to have to define what they are. So these are terms that we'll be working with very, very soon, and we'll be using them throughout our journey into the MOS and then into the MOS MOSFET. And of course, because they bend up, the metallurgical junction is less N-type than the bulk. See here is positive fixed ions. These are phosphorus ions which have given up an electron and become positive. Therefore, we have positive over here. We have a negative, that's where the electrons went, into the metal. They crossed the metallurgical junction, which is right here. And so there is a surface density right at the surface of the metal, which is negative, positive, negative. Therefore, the electric field is right to left in the negative direction. Okay, the affinity is the difference between the conduction band in either the silicon or the metal, and the free electron level is 0. For the metal, it would be this point right here up to this point right here. Okay, so just a word about the difference between semiconductors and metals. In semiconductors, we have 3 conditions. The electrons can be in the valence band where they're tightly held. They can be kicked up to the conduction band where they become mobile, or they can be completely free of the silicon at the level E0. In metals, it's a little bit simpler. They can either be in the metal, in which they are perfectly conductive, or they can be completely free of the metal, which they're up here in the level E0, and they're no longer in the metal. That's called the photoelectric effect, and that was discovered by Einstein in, I believe it was 1905. And the other issue is that the amount of band bending, this guy right here, this how high it is, how deep it is, how large it is, what the width is, all depends on the difference between the metal work function and the silicon work function. If they are the same, there's no band bending, and it's not even a rectifying junction. Okay, so that's basically what we have, and we've seen that in the metal semiconductor. We've also seen exactly the same thing in the p-n junction. So there's no difference. The only difference is in the p-n junction, it's always rectifying the Schottky barrier. If the metal work functions don't work out right, then it's not necessarily a rectifying junction. Now let's go to P. In the P, the bands bend down rather than up, and the metal work function must be less than the silicon work function in order to have a rectifying junction. The internal field is left to right. Why? Because in this region right here, which is the depletion region with W, there are negative fixed ions. And negative fixed ions means that this part is negative and holes are transferred from, lots of holes in the P silicon, they're transferred from the silicon into the metal, and then there is a surface density of holes right at the metallurgical junction. So plus here, minus here, the electric field goes from plus to minus. So all that is in the way of review, and hopefully that is not something that's terribly difficult to understand at this point. Again, as the work function difference increases, the band bending increases again, and exactly the same issue. And I should have mentioned this in the N-type, because it's same for N as well as P. It will, the Fermi, I should say, the band bending will increase until the intrinsic level touches the Fermi level. And at that point, there's a possibility, for example, in the N, if the intrinsic goes up and just touches the Fermi level, there's a possibility that electrons, or I should say holes, not electrons, holes, and they're minority carriers, but they do exist, that they will be attracted into the point right at the surface. And of course, right here, there's a surface density of electrons. So when a hole, if it is attracted, if the Fermi level goes underneath the intrinsic, there's a possibility, like I say, that a hole could be attracted. And once that hole meets an electron at the interface right here, it recombines, and therefore we cannot go further than the intrinsic value crossing the Fermi level. Same thing over here for exactly the same reasons, except here there would be electrons which would be attracted to the metallurgical junction, which they would meet a hole. Well, the same thing happens when a hole meets an electron, boom, they recombine and they cancel one another out. We can, however, have a situation where if we had a barrier here, then they would not recombine. And of course, that's the whole idea of a metal oxide semiconductor. We put an oxide barrier to prevent that recombination. Okay, so moving right along, now we apply an external bias to the device. And again, this is still metal semiconductor or Schottky. And we can go with the N-type first. And we're going to apply a bias which reduces the, or is, I shouldn't say reduce, but is in opposition to the internal electric field. That is called, in fact, that's the definition of a forward bias. And that would be a negative voltage to, I'm sorry, that would be a, I always get these things confused. Let's see if it's positive or negative. Okay. The internal field goes from right to left. In this particular case, we're actually applying a reverse bias because it is in the same direction as the internal field. And that would be a negative bias to the metal compared to the silicon. So if we apply a negative bias to the metal, we have a positive bias to the silicon, plus to minus, right to left, and that is exactly the same direction as the internal field, and that would be considered a reverse bias. So the band bending will increase or decrease? It will increase. That's the definition of reverse bias. Band bending increases, W increases, and if we applied a forward bias, this arrow would point in the opposite direction and the band bending would decrease. And again, basically what I'm saying right here is if we apply too much, well, I should too much, but if we apply a larger and larger negative bias, there's a pretty good chance that the Fermi level will dip under the intrinsic, and that can't happen because then we would have recombination. But of course, if we had a barrier to prevent that, we could have a situation where the surface right here, the metallurgical junction, surface between the metal and the silicon would actually invert. And that, of course, is, again, the whole idea of an NMOS type structure. Okay, let's see what happens when we form the metal oxide semiconductor structure. So here we go. We have metal, we have oxide, and we're going to generally use the P-silicon. Although we'll be doing a little bit with N-silicon, P-silicon is something we'll probably standardize on, and that is consistent with most textbooks. So we put these three things together, 1, 2, 3, and what happens is nothing, because there is no way for charge to transfer from the silicon to the metal. We have this huge barrier. However, if we connect the back end of the silicon to the metal, then we can get charge transfer along this connection here, and we can form a equilibrium structure. In this case, nothing happens. In this case, we put the three layers together, and we do get equilibrium. And here we are. Okay, so now we have a P-silicon, and we have a situation where we have a external bias source. If the external bias source is 0, then we're just talking about the work function differential between the silicon and the metal, which will determine to a large extent the band bending. But if we, in this case, since it's P-silicon, we have negative ions in the depletion region and positive on the metal. So the field goes from left to right, and reverse bias would increase that. So reverse bias, we would make the metal more positive, and forward bias, we would make the metal less positive. So those where those two arrows are coming. So here in this figure 17.6, we're just applying an external bias, and the issue is that we can have a much greater range in an MOS structure than we can in a MS structure. And the reason is, in an MS structure, for example, in forward bias, say more than 0.6 or 0.7 volts of external forward bias, we're going to get a large forward current. And on the reverse side, if we put too much reverse bias, we eventually have the situation where the intrinsic level touches the Fermi level in the silicon, and we can't go any further. There are no such restrictions on the MOS structure. So we can change the band bending to a much greater extent in this structure than we can in the metal semiconductor structure. Now let's apply a small negative bias, and let's see, negative bias is, here it is, forward bias, which is negative, and here we see the band bending decreases. The barrier is almost gone away, which is characteristic of forward bias. The external field is opposite to the internal field. Okay, so one other point I want to make here. There is still band bending, even though it's forward bias. The band bending is eventually going to go away completely, but there still is an electric field here, and the electric field points from left to right, and there's also an electric field across the oxide. Now, the total field would be from the metal to the silicon, and it's split, not split equally, but it's divided between the oxide and the silicon. So because it's divided, I can't regulate the field here independently of the field here. They're both in the same direction, and that's why the bands bend up in the oxide, and they also bend, well, actually they bend down, going from bulk to going to the interface, but they bend in such a way that we have an internal field in left to right. But the point is the slope. That's really what I wanted to say. The slopes are the same. Well, no. The slopes are the same general sense, but they're not the same in magnitude, because the slopes will depend on the permittivity, and we'll see that right here. So that's important. The sense of the band bending, or the talk about band bending in oxide, it does bend, is the same as the bending in the silicon. It's the same direction, although not the same magnitude. Okay, and that's basically what we're saying here. The voltage appears both across the oxide and the silicon, and they bend in the same direction for the oxide and the silicon. And of course the reason is we have a 1 voltage here to here, and it's split between the oxide and the silicon surface. Okay. All right, so now we're going to get a little bit more deeply into these things, and we're going to look at specifically metal work functions. So here is a table of metal work functions. We saw this a little bit in chapter, I believe it's chapter 8. We talked about the Schottky. The main metals that we'll be considering are aluminum, possibly titanium, and you can notice that the nickel work function and the gold work functions are much bigger. So if we put aluminum metal, or we have aluminum metal for our metal, we have a work function of about 4.05. The silicon work function is about 5, and the reason is that this is again for P. So if you look at the work function for P, it is half the band gap, that's 0.56, plus from the intrinsic to the Fermi level. So if we are 10 to the 17th, which is a very good number, that's the number we'll be using as kind of our default number for the doping in the P silicon, then we'll have 0.42 plus 0.56. And where does this 4 come from? That's the affinity of silicon. So we add all those guys up, and we get 5 electron volts. And since the aluminum is 4 electron volts, the work function difference is just about 1 volt. And that's really an important number. However, if we use gold, God forbid we should use gold and silicon, that's a terrible, let's say nickel, 5.1, then instead of having a rectifying situation, for example, in a metal semiconductor or a Schottky, we would have a non-rectifying. In the case of the MOS structure, instead of the bands bending down, they would actually bend up a little bit, and we're going to see that in just a bit. We could also use, instead of aluminum, we could use N++ silicon, or degenerately doped silicon. Now, why would we do that? Well, we're going to get into that a little bit later. But if we use degenerately doped silicon for the metal, we would have a work function. Well, let's see. The Fermi level, if it is degenerately doped N++, the Fermi level would be right at the conduction band, so that the work function would be approximately equal to the affinity, which is 4 eV, and that would be exactly the same as using aluminum. If, on the other hand, we used P++ silicon, then the Fermi level of P++ would not be 0.42 below intrinsic, it would be 0.56 below intrinsic, and we would have about a work function of about, this is wrong, this should be 5.1. Sorry about that. Okay, now it's right. Okay. So for aluminum or for silicon, we have a work function difference of about 1 electron volt. And that is a really big deal. So let's look at these, let's look at the energy band diagram for this specific condition. Now, I said an equilibrium for these conditions. What conditions? 10 to the 17th doping on the p silicon, acceptor doping, arsenic, or boron. But really what I should say, or I should have said, is with 0 applied bias. That's perhaps a little bit more correct here. So I'm going to change this and make this, instead of saying in equilibrium, we put perhaps parentheses. Let me see if I can do that right now. No, I'll figure it out later. No applied bias. I wanted to put in parentheses here for no applied bias. Okay, so for no applied bias, we have a situation where we have, for P, we have minus charge in the depletion region, positive charge at the metal oxide interface. We have the bands bending from left to right in the oxide, and the bands bending from left to right in the silicon, and that's kind of a big deal. Okay, the presence of charge between the metal and the silicon implies a voltage drop. There is a voltage from the metal to the silicon, even though there's no externally applied bias. However, I should point out, and this is going to be implicit in everything we do, there has to be a connection between the back end of the bulk to the metal. So there's an imaginary wire here, but there's no externally applied bias at this point. Okay. Now, the question is, I'm going to apply a bias, and I want to know how much bias does it take in the forward direction to make this barrier, to make this band bending completely disappear, and to make the bands continuous and flat, so that the band bending will go away here and the band bending will go away on the oxide. Something we could not do in the metal semiconductor structure, because there would be a big forward current. Okay, so let's see how that works. And we immediately see that we have a problem. And the problem is that I've got a metal to silicon work function difference of 1 eV, 1 volt. However, does that mean that I apply 1 volt external forward bias and the bands will flatten out? Well, I've got this oxide here, and this oxide has a certain thickness. So it's not clear at all that putting 1 volt of forward bias is going to make these bands go away. Now, let's do a thought experiment. Let's imagine that the oxide is so thin that it essentially disappears. Now, that's not possible. It can't be so thin. Well, actually, I should make a point in saying, why can't it be so thin as to eventually disappear? For example, 1 angstrom. That's so thin it doesn't exist, essentially. And the reason is that electrons and holes or waves, anything below 15 or 20 angstroms, which is to say 15 or 20 atomic dimensions, will be so thin that the electron will just tunnel right under it. So quantum mechanics, unfortunately, limits us to a thickness of the oxide of somewhere around 20 to 25 angstroms, and that is about the state of the art. Today we're going to be talking about that in somewhat more detail later on, because we want to make this oxide as thin as possible, and that will become clearer in our future discussions. But let's go to imagine, okay, that somehow we have a magical barrier here, and that magical barrier is so thin that it essentially doesn't exist, and all it does is prevent charge from moving from the silicon across to the metal. Now, in that case, since I have no barrier, I apply 1 volt of forward bias, and these bands will exactly flatten out. And that would be a flat band condition. Can't do it in a metal semiconductor structure because I can't make an infinitely thin barrier. So this is just a thought experiment. Okay, now we return to a more realistic. Okay, now we can let it out and let out our. We were holding our breath there, and that was really kind of a silly thing, but it's just to illustrate the point. And let's say that the oxide and the depletion capacitance, there's an oxide capacitance, there is a depletion capacitance, and let's say, in a realistic sense, that they're the same. They're equal. In this case, this realistic case, if I'm applying a voltage, if I don't apply a voltage, I still have a voltage, this internal electric field, and then I apply either a reverse bias or a forward bias, I have anyway, in either case, in all cases, I have a voltage from the metal to the silicon. But if the capacitances are exactly equal, I will claim, and I think it's reasonable, that I drop 1/2 of that voltage, whatever it is, across the oxide, and I drop 1/2 across the silicon. So what happens in this case is the band bending is less. The band bending, let's say, this is with 0 applied bias. If it's 0 applied bias, I don't get the full 1 volt across the silicon. I only get half of that, because half is dropped across the oxide. So instead of having 1 volt of band bending, I have 1/2 volt of band bending. Now I apply the same 1 volt external forward bias. Half goes across the oxide, half goes across the silicon, which is to say I've got 1/2 forward bias across the silicon, exactly what I need to make the band bending completely go away. So in both cases, in the unrealistic case or in the realistic case, if I apply 1 volt of forward bias to the structure, the bands flatten out completely, and I get what is called the flat band voltage. This is the voltage, the external voltage on the gate is equal to the flat band voltage, the voltage that I need to make the bands go away, and that is exactly equal to the metal work function minus the silicon work function. Sometimes I'll put in the SS or SI, but it's the same thing. And the critical issue is, and I should probably have put this in bold letters, where is it? Here it is, right here. It is independent of the oxide thickness. So I was going to make this bold. Let's see if I can make this bold. And bold right there. Independent of the oxide thickness. So if the work function difference is 1 volt, then I need 1 volt of forward bias to make the bands go to flat band. And in flat band, there is no charge here, and there is no charge here, and the bands are exactly straight and horizontal. And that is a really, that's a really big deal. So one last quote. Well, let me just go back here. Where's the external bias? Here it is. So here's the external bias. This is called VG. This is the bias we apply to the metal with respect to the back end of the silicon. And if I get to a point, if I apply a forward bias of equal to the difference of the work functions, then I get flat band. Now what sense is that? Plus or minus in p-type silicon, which starts out in depletion? Well, we can go back right here. Go back here. Forward bias, less positive, more negative. So I have to apply a voltage of minus 1 volt to go from the depletion condition where the work function difference is 1 volt. I apply a negative bias, and that would be a forward bias, and that gives me flat band. Okay, and again, for same conditions, 10 to the 17th, the work function difference of 1 volt. For N-type silicon, then I would apply a positive voltage of 1 volt to flatten out the bands in N-type silicon. And what would I have for N-type silicon? Well, there I would generally want to have a P++ silicon because P++ would give me a metal work function of 5.1, and the silicon work function would be about 4. So actually about 4.1, 4.2. So that would give me the same exact conditions, and then I just apply a positive voltage. So we don't have to remember that. We just remember forward and reverse. That takes care of everything. Okay, now before we end, let's return to the NMOS structure with P silicon, and we apply a negative bias of 1 volt. We get flat band, but suppose we keep going. We say, why should I stop at minus 1 volt? Keep on going. And if I keep on going and apply a bias which is more negative than 1 volt, then what happens is I start attracting holes. Don't forget now, with a negative bias, instead of being positive here, I have negative charge here. And when I went to flat band, everything's flat, there's no charge. And then I keep going, so I have a minus charge on the metal, and that attracts silicon, and the bands, instead of bending down, they were bending down. We applied a negative voltage of minus 1 volt. They became flat. I applied, say, 1.2, 1.3 volts. So instead of bending down, they start bending up. becomes more P at the silicon, and then basically all I have is a capacitor. So that's where we're going to end. We're going to take this up next time, but we can write immediately, since we know that the charge is equal to the capacitance times the voltage. What capacitance are we talking about? The oxide capacitance. There is essentially no band bending in the accumulation mode. In the silicon, the bands bend up just a scotch, but the only real capacitance we have is the oxide. And this guy, instead of going from left to right up, it will go left to right down. So that would be something that we're going to call the accumulation mode. And the accumulation mode is the gate voltage difference between flat band and what we need to make it even flatter. Well, I should say flatter, to bend the opposite direction from depletion. In our case here, the bands will be bending in the up direction. So if the flat band voltage is minus 1 volt and the gate voltage is minus 1.3 volts, then we'll have this total here will be minus 1.3, and we can have, in that case, a charge accumulation of the oxide capacitance, which is relatively straightforward to figure out, multiplied by that gate voltage as given by equation 17.2. Okay, I was going to stop here, but let me just do one more little thing here. Okay, so basically we started out with depletion. We applied the flat band voltage to bring us to a condition of flat band. We keep going, that's this arrow right here, we keep going in the negative direction if it's P silicon, and we arrive at the situation called accumulation. And we'll explain that a little bit more. However, we can go the opposite direction. We could start, for example, with accumulation. We apply a flat band voltage to bring us to flat band condition, and then we go to depletion. This part over here is what is going to occupy our resources for quite some time, but basically we'll be reviewing this part right here. We'll be saying a lot more about that in our next session. So let's now jump down to the very end. Oh yes, okay. So the last video clip, I'm going to start with another video clip in our next session from the Barber of Seville. It's a wonderful opera by Rossini, and let's listen to the overture to the Barber of Seville by Giacomo Rossini, and we'll see you next time.